Hello, welcome to Wednesday's lecture. We'll get started in just a second. We're continuing on with acid and bases with, excuse me, which should be chapter 8, I believe. So again, we'll get started in just a minute or two and continue on. And like usual, if you have any questions, feel free to type them in the chat box. And again, even if I happen to move past a slide, you can still type your question. I'll go back and make sure I answer your question if you have it. All right, so like I said, we are going to be continuing on here with chapter 8, which is acid and bases, and we sort of left off with pH. Remember that the pH scale goes from 0 to 7 to 14, and below 7 is acidic. Above 7 to 14 is basic. So above here, I get my thing to work here. It's been kind of bad all day. It's basic. A little bit better so far. And then again, as we talked about right there, dead on 7, get to 7, is our neutral. So that is our pH scale, and that's what we can use to measure acidity. So remember that if it's really not 7, again, if you could, make sure you keep your camera off. Thank you. So if it is below 7, it'll be acidic. If it's above 7, it'll be basic. And right there on 7 is neutral. And the reason for that really goes to what we were talking about also. Previously, we saw that Kw, which is the H plus concentration, times the OH minus concentration equals 1 times 10 to the minus 14. And that relationship allows us to calculate either the H plus concentration or the OH minus concentration. The H plus concentration is essentially the acid part. The OH minus concentration is essentially the basic part of the solution. And again, you can use this to calculate either one. It's essentially the same calculation, no matter which way you do it. You take 1 times 10 to the minus 14 and you divide it by the other concentration. So the relationship between H plus and OH minus is as one goes up, the other goes down. So as H plus goes up, the OH minus concentration will go down. As the OH minus concentration goes up, the H plus concentration will go down. So that is the relationship. They work equal to each other in that sense. As one goes up, the other goes down. And if they are equal to each other, then it would be a neutral solution. And if they are equal to each other, that means that you would have the H plus concentration equals the OH minus concentration. And that would be 1 times 10 to the minus 7, which if we calculate the pH is equal to minus the log of the H plus concentration. So that's also something that we learned. And if you put in 1 times 10 to the minus 7 into that equation, what you will see again is you will get a pH of 7. And that's why, again, technically neutral is dead on 7, because the H plus concentration at that point would be 1 times 10 to the minus 7, which would give you a pH of 7. A relatable scale that we also talked about is pOH. So POH is equal to minus the log of the OH minus concentration. And a nice relationship between these two is that the pH plus the POH will equal 14. So this gives you a couple of options, and that's not plus or minus, it's actually just plus. So sorry about that. My pen's been not so great all day. So the pH plus the POH will equal 14. So that allows you, if you have the H plus concentration, you can calculate the pH. And if you want to find the POH, you can simply just subtract 14 from it, and vice versa. If you are given the OH minus concentration and you want to calculate the pH, you could first calculate the POH and then calculate the pH by subtracting 14 basically for it. So it gives you some options in terms of how you could solve some of these problems by doing that. We also talked about that you can, if you have the pH, so if you have the pH, you could get the H plus concentration from that. And you could do that by taking the inverse log of the minus pH, and the inverse log, when you put it on your calculator, usually will pop up that 10 and caret. And you could use that to calculate the H plus concentration. You could do the exact same thing with the POH. So with the POH here, you can do the POH, you could get the OH minus concentration from it. It's the exact same calculation, which is really good. It's the inverse log of the minus POH. Don't forget the negative there. And again, that will put on your calculator usually a 10 and a caret and minus POH. So these were several of the sort of formulas that we talked about in terms of this chapter and how to calculate different things. You can also still use KW to calculate things like H plus and OH minus, but if you have the pH or POH, it also gives you some options as to how to calculate it. The other important thing that we talked about was that for sure, when you're asked a sort of simple question of, is the solution acidic, basic, or neutral, the answer should only be one of those for that solution. So things can only be either acidic, basic, or neutral. They can't be all three. And it's very common. Again, sometimes people give the same answer or different answers for the same solution. Like, I think it's acidic, but I also think it's basic as well. And that usually happens because of the pH and POH. People look at the pH and go, it's less than 7, so it's acidic, but then they look at the POH and go, it's more than 7, so it's basic. When you're trying to determine if it's acidic, basic, or neutral, what you want to do is always look at the pH value. And that's because most people understand or remember the actual pH scale that we see up on top there. And that's the one most people think about. So always look at the pH when you're trying to determine acidic, basic, or neutral. And again, you'll be in the right direction there. Any questions on any of that we talked about last time? Or maybe last couple of times? Okay, so we left off, I think, on an example here. So why don't you take a moment? I don't think we did this one. So why don't you take a second here, and we want to calculate the pH. I'm sorry, we have the pH, that is 3.14. We want to know what is the H plus concentration. And so see what you come up with here. So just take a moment and see. Okay, so we are given the pH. So again, a reminder that if you are given the pH, you can get the H plus concentration, and that was doing what we just saw, which is equal to the inverse log of the minus pH in this case. So since we do have the pH here, that's essentially what we want to put into our calculators. Again, a reminder that the inverse log is basically the shift button on the top left of your calculator, or most calculators are the second button that's up there, and the log button. And if you do that, again, it typically will put something like 10 in a caret. Again, you want to make sure that it is negative 3.14, and you will get a concentration of 7.2 times 10 to the minus 4. Actually should have units, so it should say molarity there. So it should have the big M next to it. Any questions on that? Also, a reminder of sort of significant figures and decimal places. So when we have a pH or a POH, this number here had 2 decimal places. So what that means is when we go to the concentration, we will have 2 sig figs. Yeah, so I'll do my best. Like I said, unfortunately, my pen is going crazy here today, but we'll give it a go. So to do the inverse log, which I think is what you're asking, how to punch that into your calculator. Again, usually on the calculator, top left corner, there's like a second button or a shift button. And you usually want to hit that, and then you usually want to hit the log button next. Because usually above the log, there'll also be like a 10 to the X that you usually will see. So you want to hit second and log, and then you want to make sure that you use your negative button. So you want to use your negative button, not your subtract button. So make sure that you find your negative button there, which is, again, on most of these, something like that, or it may look like that. And then you want to go 3.14. Again, if you have a display calculator, usually it will pop up something that will look just like this when you do all that. And then obviously you want to hit equals. Remember that, as we talked about as well, if you should have a non-display calculator, and again, if you're not sure if you do or not, you can just hit log. And if you hit log and it says error, you have a non-display calculator. But if you have a non-display calculator, you need to put all these formulas in backwards. So you need to go this way, which means if you have a non-display calculator, you would actually first put the number in, like 3.14. You would hit the negative button and then hit the second log button, and you should get the answer. So again, if you have a display calculator, you do it in order, just like the formula. If you have a non-display calculator, you have to go backwards. Other questions on that? Okay. So why don't you try this one here? Give it another practice in case you need here. So we have a pOH of 5.67. What is the OH minus concentration? You're welcome. All right, so again here, we pretty much want to do the same calculation, regardless really of which one you have. If you have the pH or the POH and you want to get the concentration, it's really the same calculation. So here it's going to be, again, the inverse log of the minus POH. Missed that pretty bad there. So the minus POH there. And again, that should also put on there a 10 and a caret and the minus POH. And if we do that, again, making sure we use our negative button, not our subtract button, again, we will get a concentration of 2.1 times 10 to the minus 6. Again, should have the big M next to it, which is molarity. Not the underline, but just the big M there for molarity. Any questions on that? Again, same idea. We have in the POH value, we have 2 decimal places. So that should get us 2 significant figures down here. Any questions on how to do that calculation? So if we were asked, is the solution acidic, basic, or neutral? The answer should actually be basic in this case. So the solution, by the way, would be basic. And it's basic because the pH would equal 14 minus the 5.67. And again, if we do that, we do get over 7, and that's 7.94 or 93, something like that. So if we take 14 minus or 5.67, gives us 8.33. I'll do the math right there. Might be better. Gives us 8.33, which is a basic pH. So remember, you want to look at the pH, not the POH, when you're trying to determine is it acidic, basic, or neutral. Any questions on those there? Okay. So what happens if we actually have a strong acid and we want to figure out the pH of it? And up until this point, most of the time we're trying to figure out the pH or the POH, we're sort of given more of a generic concentration, like the H plus is equal to this, the OH minus is equal to this. But if we do have something that's actually a formula of a strong acid, remember that there are some strong acids, HCl, which is hydrochloric acid, HNO3 is nitric acid, HClO4 is perchloric acid, H2SO4 is sulfuric acid, HBr, which is hydrobromic acid, and HI, which is hydroiodic acid. These are all examples of strong acids. And strong acids are essentially strong electrolytes, as we talked about earlier on, which means when it's in solution, something like HCl would 100% pretty much break apart into our ions. So 100% of what we would have in the solution would be these two guys here. I missed. And that's 100% of what you got. And remember that it is the pH is equal to minus the log of the H plus concentration. Try that again. H plus concentration. Sorry about that. And it is the free H plus in the solution that really affects the pH. So really added these two things, the only thing that you would need to figure out is the concentration of the H plus that's in that solution. So if I had a 0.1 molar solution of hydrochloric acid, because it will 100% break apart into ions, that essentially means that what we would have is 0.1 molar H plus. Remember, the way we can figure that out is this is the concentration of the whole thing. And it is a 1-to-1 relationship in terms of how the H plus breaks apart. So you would take 1 times that concentration, which would get you 0.1 molar for the H plus. You didn't need it here for this calculation, but to get that guy, same idea. It's a 1-to-1 relationship in terms of how it breaks apart, which means the concentration for the chloride ion would also be the same. Again, not needed here because really pH is all based upon the H plus concentration. So since we know the H plus concentration, after breaking it apart, we essentially can put it into our pH equation, and we will get a pH of 1.00, which is definitely a acidic solution, definitely at a pH of 1.00. So sometimes you'll be given an actual formula for an acid, and that formula, you need to figure out the H plus concentration. The good news is in this class, you will only be given an acid that is strong. So if you're given a formula for an acid, it is a safe assumption to assume that it is a strong acid, which means all you pretty much have to do is figure out the H plus concentration and then stick it into the pH equation. So the reason you won't get any weak acids in this sort of chapter in this class is because those calculations are much longer. So they're very long and a lot more steps involved in it. So if you see a formula for an acid in the book, it's most likely going to be a strong acid. And by the way, this would also go for a base. So if you're given a formula of a base like KOH, which is a strong base, it will break apart into K plus and OH minus. Again, here, the important part would actually be the OH minus, as that will allow you not to get the pH, but you would be able to get the POH and then figure out the pH from it in that case. So if you're given a formula of a base and asked to calculate the pH, you could probably safely assume that it is, like I said, a strong base as well. And again, in that case, you'd be interested in the hydroxide concentration, and then you could get to the POH and then to the pH. Any questions on that? So I'll let you try this one. So see what you come up with here. We want to know what is the pH of 0.025 molar HCl. So again, here, looking at this one, HClO4, which is perchloric acid. Again, it is a strong acid, which means when it goes for a swim in the solution, it is going to 100% break apart into these guys. And again, for the pH, the only really important guy here is the H plus concentration, which means if I know that the whole thing is 0.025 molar, Again, as we talked about in solutions, it's a 1-to-1 relationship between the HClO4, the entire thing, and the H plus concentration, which means the concentration of the H plus will be exactly the same. So that means we really do have our H plus concentration, and we could stick it into our pH expression, which would be minus the log of 0.025, and that will give us a pH of 1.60, which is acidic, and what we would expect since it is obviously an acid. Same thing here, we have two significant figures in this number, and that gives us 2 decimal places in the pH value. So remember, significant figures in the concentration, 2 decimal places in the pH or POH. Any questions on those calculations there? All right, so the last thing we're going to talk about in this section or chapter is a buffer. Good talk. Let's go back and talk a little bit more. So a buffered solution is a solution that essentially will resist changes in the pH, even if you decide to add some acid or base to that solution. So what we're talking about when we have a buffer solution is a buffer is able to resist that change in pH. When we talk about that change in pH, we're talking really about big changes in pH. When we add either more acid to it or base to it. So very common people, when they see buffer, think about a buffer is they think it's a neutral solution. So they think it is a pH of 7, for example. It's a neutral solution. And that technically is not what a buffer is. Although a buffer can be neutral, so you can have a buffer that is like a pH of 7 and is a neutral solution. You can just as easily have a buffer that is acidic, and you can have a buffer that is basic. So you essentially can make a buffered solution at any pH you choose. So what it essentially means is once you make that solution, let's just say that solution that you made had a pH of 4. And if you take that solution at a pH of 4 and that was a buffer and you add acid to it, what that means is the pH of that solution after you add the acid should still be around 4. It will go down a little because you are adding acid. So maybe it'll go from 4 to like 3.9, maybe 3.89, something like that. It'll go down a little bit, but it will not go down from say, or start at 4 and end at like a pH of 1. So you won't have that big jump in pH. Remember that as the pH changes by 1, you're changing by the power of 10. So like times 10 to the minus 3, 10 to the minus 4. So every time you go by a power of 10, the pH is actually changing by 1. So if you added acid to that buffer solution at a pH of 4, it would pretty much stay at a pH of 4. Same deal if you added that buffer to that buffer some base. What that means is that buffer solution will maintain that pH of 4. It will probably go up a little bit. So if you were monitoring it with like a pH meter, you would see the pH go up a little bit. So maybe it goes to 4.1, maybe it goes to 4.05, 4.09, but it will not go from a pH of 4 to like a pH of 12 if you add base to it, if it is a buffer. So that's what a buffer means. Again, does not necessarily mean the solution is neutral, but what it means is it's able to maintain the pH of where it's at if you decide to add additional acid or base to it. Any question on that? So now we're going to talk about how it's able to do that. And the reason it's able to do that is because of what makes up a buffer. And what makes up a buffer is what's on the bottom here. It essentially can be a combination of one of two things. You can have a combination of a weak acid and its conjugate base. And sometimes that's referred to as the salt of its conjugate base. Or you can make a buffer of a weak base and a conjugate acid. And again, it's sometimes referred to as the salt of its conjugate acid. And both of those things are in there to begin with. So the importance of it being actually a weak acid or a weak base is because, as we talked about, a weak acid or even a weak base, they are weak electrolytes. And basically, what that means is, if you remember, that is a certain type of reaction that we've seen that has those arrows that head in both directions. So, for example, something like acetic acid, which is this. Acetic acid is the acid that you find in vinegar, is a weak acid and a weak electrolyte. When it is in solution, it will break apart into H plus and acetate. And because this is a reversible reaction, like we talked about, it will eventually set up what we talked about in that one chapter, which was an equilibrium. And what that means is, in the solution, if you had acetic acid, which is a weak acid, it will set up this equilibrium and mean that in this solution, you will have this guy present, and you will also have this guy present. And this is our weak acid, and this is his conjugate base. And because both of those things are in the solution to begin with, they're able to basically connect and take care of any acid or base that you essentially will put into that solution. So that's a very important part of it, is in the solution to begin with a buffer, the weak acid and its conjugate base are both in the solution to begin with. Are, if you made it out of something else, like the weak base and its conjugate acid are both in there to begin with. Any questions on that? Yeah, so maybe try to adjust it as best you can. In terms of the voice, I apologize. It's been like that all day with all my lectures. I think it has something to do with sort of the meeting here and the Zoom software. So try to adjust it the best you can. And, you know, I'll do my best, but everything's set the same way as I've had it all the time. So, you know, I think it's just something weird today. That's why my pen, if you've noticed, is kind of weird as well. There's something not so right today in terms of the meetings. I've had it all day and stuff like that. So that's why when I'm writing, it's kind of weird looking too. There's like a delay on my side as well. So I think that might be what you might be hearing or not hearing and stuff like that. So hopefully it will kind of stabilize, but it's been a little unstable for most of my lectures today. And that's why the pen is a little out of control as well. So that's why I'm switching from the mouse to the pen. It's just, there's like a big delay. All right, so in terms of buffers, both of these guys are in that solution to begin with. And and that's incredibly important in terms of how it's able to function. So let me go back to this screen, which is empty. I'm going to give it the college try here with my not so great pen today. So So let's say we took a buffer like, not that, come back. There we go. So let's say we took the buffer like acetic acid and sodium acetate. Now, when we look at a buffer like this again is our weak acid and our conjugate base. And this is what will make this what is sometimes referred to as the salt of its conjugate base. And it's really a salt because of, if I can get this thing over there, come on today. This is a salt because of the sodium that's present. So this sodium here being present, not really doing anything in terms of any reaction that's taking place. It's really just there to balance out the charge. And that is because if you have sodium acetate in solution, it's a strong electrolyte, so it will break apart into Na plus and CH3 COO minus. So really sodium acetate is the source of acetate, which is the conjugate base. But again, that's why sometimes it's referred to as the salt, because you'll see a sodium with that guy. You'll see like a potassium with that guy. You'll see something like that sort of with it. So really what we have here when we think about this buffer is we have a acid part and we have a base part of the buffer. So when we take something, for example, before we add it to, say, this buffer, we're going to add it to water. So if we take water, which is not a buffer, so water, which is not a buffer, and if I take hydrochloric acid, which is a strong acid, and add it to water, what I'm going to get is H plus and Cl minus. And again, 100% of what I'm going to have in that solution is H plus and Cl minus. And essentially what that means is you're going to produce a lot of our H plus really fast. You're going to produce a lot of this H plus really, really fast. And when you produce a lot of that H plus really fast, what we would expect to happen here is we would expect to see a big change in that pH. And we expect to see a big change in that pH because remember, as the H plus concentration, the pH will go down. So when we produce all that free H plus, this would be an example where you would perhaps see the pH go from, say, a pH of 5 point something with water all the way down to maybe a pH of 1 if you added HCl to water. So you would see a pretty big jump in that pH when you add that acid to it. And the same thing would happen if we added something, say, like sodium chloride here, sodium hydroxide, I'm sorry. And sodium hydroxide is a strong base, which means it's going to 100% break apart into sodium ions plus hydroxide ions. And 100% is what we're going to have here, just like above. But the difference here is we have 100% of a lot of OH minus. OH minus is made very quickly. And if you remember the relationship between OH minus is as the OH minus concentration increases, we will see the H plus concentration go down. And if the H plus concentration goes down and the OH minus concentration goes up, that means that we will see the pH go up as well. So in this case, you would see a similar sort of thing occur. You would see, say the pH of that water was 5 point something to begin with. You add some sodium hydroxide to it. Because you made a lot of free OH minus really quickly, the H plus concentration will go down and the pH would go up. So this would be a situation where perhaps the pH goes from 5 to say maybe a pH of 9 or maybe a pH of 10, depending on how much you add in that particular case. So when we add acid or base to a non-buffer situation, we will see these really big kind of jumps in pH. So you'll see a pretty good change in the pH. Again, when you add acid, you would expect the pH to go down. When you add base, you would expect the pH to go up. Any questions on what happens in a non-buffer situation? So the next thing we're going to talk about, and again, if you do have questions, feel free to type them. What we're going to talk about now is what happens if we add those exact same things that we added to water. If we add both the HCl and the sodium hydroxide, if we add those to our buffer that was up here. So we're going to use this guy as our buffer. So using that as our buffer, we have our CH3COOH, which is our acetic acid, and that's our acid part of the buffer. And the other part will be acetate, which I will just do like this. And this is the base part of the buffer. Here I left off the sodium ion. Again, you will oftentimes see this as sodium acetate. Again, the sodium really is just a spectator ion. It's just hanging out and watching. It's not really involved in the reaction. But if you want to leave the sodium on, you can. It, again, will have no effect on what's happening. So if we take this buffer and I decide I'm going to add HCl to it, and HCl, it's the same thing we just added to water. HCl, which is an acid, the HCl which is our acid, will then react with the base part of the buffer. So it's going to react with the base part of the buffer. The way you know that is they're called acid-base reactions. So when you add acid to a buffer, it will then react with the base part. And when it reacts with the base part, and again, if you want to leave the sodium in there, you can. So if we do this, and it might help you sort of see what's going to happen in this reaction if you do. This is a positive, negative guy. This is a positive and negative guy. That is going to be a double displacement reaction. So what's going to happen is our H will hook up with the acetate. Our sodium will hook up with the chloride, just like we talked about with reactions. And when that happens, what we will make is acetic acid on this side. And we made some sodium chloride on this side. So that's a C. Any question on that reaction? So already you hopefully see it's a little bit different. We do see a couple things. We see that what we made on the product side when we added this acid to the buffer was we actually made this guy right here, which is acid, which is acetic acid, which was actually part of the buffer to begin with. And that is always the case when you add acid or base to the buffer. It will react with one part of the buffer, but then it will make the other part of the buffer. So since it made more acetic acid and the acetic acid was there to begin with, that is not going to mess up the pH at all. Something like sodium chloride, which is over here, will have no effect on the pH. It is what is referred to as a neutral salt, which essentially means it'll have absolutely no effect on that pH. The most important thing that we do not see here that we do see when we looked at it, when we added the acid to water, is when we added acid to water, we produced a lot of free H plus. And if you look at what happens when you react it with the buffer, we do not produce any free H pluses. And because we didn't produce any more free H plus, the concentration of H plus remains relatively constant. And if the H plus concentration stays relatively constant, what that means is the pH will remain relatively constant as well. And by relatively constant, what I mean is you will still produce a little bit of H plus. And that's why you will still see a slight change in the pH when you add acid to a buffer, but you will not see a tremendous jump in pH, because the main thing that the buffer is able to do in this particular case is prevent all of that free H plus that you would normally produce if it wasn't a buffer. And that really is what affects the pH, because if you remember, the pH, right, is R minus the log of the H plus concentration. And that H plus concentration is the free H plus concentration in the solution. So when we add that same acid to water, we make a ton of H plus, which has a very big effect on the pH. But when we add that same acid to a buffer, we don't get any more free H plus, which keeps that original H plus concentration constant. And by default, we'll keep the pH relatively constant. Any questions on how that works when we add an acid? Now, the same effect occurs when we add a base. So for example, if we were to add that same base that we had on the other side, if we add some sodium hydroxide, which is again our strong base, when we add this sodium hydroxide, it's going to react with, in this case, it's going to react with the acid part of the buffer. So you would get a reaction of sodium hydroxide plus the acid part of the buffer, which is our acetic acid. And you also should recognize this. This is also a really double, this actually is the negative side. And when we look at this, we see a very similar result as to what we see above, a little bit different, but same core idea here. When we look at the product side, we again made the other part of the buffer, which was there to begin with. So that's going to have no effect on the pH. We made some more sodium acetate. And again, that was the original part of the buffer. But the same thing that we actually do not see here, that we do see over here, is when we added that strong base to water, we made a lot of OH minus. And as I wrote over here, as that OH minus concentration went up, the H plus concentration went down, and the pH went up. And when we look over here, we see really no free OH minus being made, which means the OH minus concentration is relatively constant. And because the OH minus and the H plus concentration related to each other, again, as one goes up, the other goes down, and vice versa. As this guy would go down, this guy would go up. So if the OH minus stays constant, the H plus concentration will also remain relatively constant. So The way a buffer really works is by exactly what we see in these sort of reactions. When you add an acid to a buffer, the acid will react with the base part of the buffer, and it will make the acid part of the buffer. But more importantly, what it prevents is free H plus from coming into that solution. And because you kept the H plus concentration relatively constant, it will keep that pH also relatively constant as well. And the same thing when you add a base to a buffer, the base will react with the acid, which I think I'm missing a C in there. Pop a C in there. There you go. It will react with the acid, and it will make more of the base part of the buffer. And the key how that works is it prevents really free OH minus from being formed. And because the OH minus remains constant, the H plus concentration will also remain constant. And as a result, the pH will remain relatively constant. So a buffer, if you did add acid or base to it, you would see a slight change. When you add acid, it would go down a little bit, but not a big change. And if you add some base to a buffer, it will go up a little bit. Again, not a big change. Big changes occur in pH when we add acid or base to things that are not buffers. Any questions on how that works? Now, essentially, give it a try here, see if we can get it to maybe work here for a second. So when you have a buffer, essentially in the buffer, a lot of times you will start with the acid part and the base part kind of equal to each other, so that when you add more acid to the buffer, what happens is it will use up some of the base, but make some of the acid part. So sort of exaggerated here. The acid part of the buffer will get bigger, and the base part of the buffer will get smaller after you add acid to it. Same thing on this side. If you add base to it, a little over exaggerated, but I'll do it that way. We'll use up some of the acid part and it will get smaller. It's really important thing. So it has to be in buffer to begin with, because then it will have an acid part and a base part that allows it to work. You could also see that there is a limit to how well a buffer will work. So for example, if we were going in this direction and you didn't read the instructions, nobody would do that, I'm sure. But if you just keep adding acid as we're going in the sort of this direction over here to this side, basically what will happen is if you keep adding acid, you will chew up all of that base in the buffer. And at some point, it will no longer be able to act as a buffer because you kind of chewed up all of it. Same thing if you did the other thing. If you added base to the buffer, it would chew up the acid part of the buffer. And at some point, it would not be able to still behave like a buffer. And that is what is sometimes referred to as buffer capacity. There is a limit to how good a buffer will work. Things like concentration are really important for it as well. Any questions on buffers or how they work? Okay. Let me see. That should be it for chapter 8. So I'll stop sharing here. We're going to go on to organic now. So that also concludes our calculation chapters. We're now going to get into pretty much non-calculation chapters. So did not like that. Let me see here. So we're going to roll to chapter 10. Again, we're skipping chapter 9, which is nuclear chemistry, and we're just going to pick up chapter 10, which is organic chemistry. All right. Give it the old try here. Try that one there, perhaps. I did not like that. Let's try it again. Difficult today. All right. Okay, let's drop that. All right, let's try it again. Let's go with that one there, maybe. All right, let's see. All right. Still does not like that. All right. You can find one of these it likes, and then we'll be able to see something. Let's go with that one. Maybe. Hey, I think you can see that, hopefully. There we go. I hope. Very temperamental today. All right. Let's do that. Let's do that. All right. All right. So we're going to talk about organic chemistry. So as I mentioned before, organic chemistry, I know you don't have it up there. Hang on one sec. Let's try to get it to go. Should really have entertaining music as I'm trying to do this. Let's see. All right, we'll go with this one, I guess. All right. That I think you can at least see, even if I can't see you. Okay, let's see. We'll go that way. And we'll try this. All right, so let's go with this one here. So organic chemistry is really going to be more about memorization. There's going to be a lot of naming. There's going to be reactions that you need to know. The good thing is, I guess, if you don't like calculations, you will never have to pick up or use a calculator in any of these chapters to do any type of calculation. Obviously, you need to find your calculator for exam 3 because chapter 8 is on it. But other than that, from this point on, for the rest of the chapters, it really is going to be all kind of memorization and those type of things. So we're going to go over pretty much all the organic. We're going to go over all the different types of organic compounds, how to name them, again, like I said, reactions and so forth. So chapter 10 is kind of an overview to organic chemistry. So it's going to kind of touch upon each of the different groups of organic molecules that we will see. And we'll go into each of those groups really in the rest of the chapters 11, 12, and 13. We'll hit pretty much all the different groups. So we'll start with usually the first sentence you see in an organic textbook, which is organic chemistry is really the study of carbon and carbon-containing compounds. Carbon, which has 4 valence electrons, as we will see, will want to make 4 bonds. And that's a really important thing to remember as we go through organic chemistry. When people start drawing organic molecules, they always want to draw carbon with thousands of bonds. They just keep throwing bonds on carbon. But carbon really should only have, obviously, only 4 bonds. Organic molecules are basically carbons, hydrogens, and oxygens. Other things like nitrogen gets thrown in there. Other things like sulfur and some other guys get thrown in there. But the basis of how organic molecules are essentially carbons attached to carbons, and usually attached to those carbons are hydrogens. So that's really your basis of how these guys are basically put together. The organic molecules are also a lot of times have non-polar aspects to them. And that is because the carbon-hydrogen bond, if you remember from bonding, whatever chapter that was, way back when. The carbon-hydrogen bond in terms of electronegativity is essentially a non-polar bond. So a lot of organic molecules are non-polar. A lot of parts of organic molecules are also non-polar as well. So organic compounds exist in molecules with weak intermolecular forces, again, because those molecules are typically non-polar. There's a lot of parts of organic molecules that are non-polar. If you remember, those are the guys that are going to use our dispersion forces that we talked about. Remember, dispersion forces are those really weak intermolecular forces where they're kind of temporarily gain charges and interact with each other. And that's typically how our non-polar organic guys are able to interact with each other. Remember the idea of like dissolves like, so things with similar intermolecular forces are able to interact well with each other. So non-polar guys and non-polar work well. And that's different than something like sodium chloride, which is an ionic compound. It's usually a solid at room temperature. A lot of the organic guys are gases at room temperatures. A lot of the first organic compounds are flammable as well. Things like methane, propane, butane. These are all things that are very flammable, and that's a very common sort of property for our organic guys. So as I mentioned before, all of the organic guys will contain carbon and hydrogen. And again, very important to remember, no more than 4 bonds to carbon. Carbon does really want to continue to make 4 bonds and really want to have 4 bonds, but should never have more than 4 bonds. A reminder as well that hydrogen should only have 1 bond. So like we see in the picture here, hydrogen should never, ever, as we talked about with bonding, have any dots. It should only make basically 1 bond. Or if you want to represent them as dots, all the bonds, you can. Again, just like we talked with Lewis structures, never dots around hydrogen. Yeah, because again, you get one of those. Yeah. Also, never double bond to hydrogen, never triple bond to hydrogen. Not sure what happened to my triple bond there, but you shouldn't be doing it anyways. Yeah. So again, hydrogen, just 1 single bond is pretty much all it should have. The nice thing about carbon is carbon to carbon, it can form single bonds, it can form double bonds, and it can form triple bonds. And those are very common organic sort of compounds. These, as we will see, are a group of organic compounds known as alkanes, ANE. This guy with a double bond is what is known as an alkene, ENE. That's where I wish my pen was working better. And these guys with a triple bond are what are known as alkynes, YNE. So these are different organic compounds or groups of organic compounds, and they're really based on what are referred to sometimes as a functional group. So a functional group for an alkane, as we will see, is the presence of just carbon-carbon single bonds, while the functional group of an alkene is the carbon-carbon double bond, and the functional group of an alkyne is the carbon-carbon triple bond. Hang on 1 sec here. Let's see there. Okay, any questions on that? All right, fix that problem. Now I can actually see if you do have questions. That's good. All right. So here's the first common couple of organic molecule. Methane is the simplest organic molecule you can have. It is one carbon with 4 hydrogens attached. Methane is very flammable. It is the gas that comes out when you light like a Bunsen burner or a stove, as you can see there. So this is our methane. Ethylene over here is used in preparation of plastic, and ethylene has, as you can see, ANE. All of this carbon has single bonds. Ethylene is 2 carbons with a double bond in the middle, and that's an alkene, which is why this guy ends in ENE. And if you look at methane, it ends in ANE because this is an alkane, has a single bond, or carbon-carbon single bond. And this is an alkene where it has a carbon-carbon double bond, ENE. So a lot of things in organic chemistry are named that way based on the group, and based on the group sort of name, based on the group name is how we kind of name these things. Some organic compounds have chains and some have rings. So this is what is sometimes referred to as a straight chain. And it's pretty much what it sounds like. All the carbons run all together, so they're all in a straight line. Sometimes the carbons will kind of connect together and make what is sometimes referred to as a ring structure. And this is the same as you will sometimes see drawn as like a triangle. And this triangle represents what is known as line structure. And in line structure, you typically don't draw out the carbons or anything like that. You just basically use lines. And you know that at every sort of intersection of where those lines come together, or every point of those lines represents a carbon. So for example, if I come down here, this represents a carbon, this guy represents a carbon, and this represents a carbon, which would represent those 3 carbons here. And that's a ring structure, so the carbons can sort of close in on each other and make a ring type structure. By the way, while we're talking about a straight chain, we could also have carbons that will, what is sometimes referred to as a branch chain. So you'll have a bunch of kind of straight carbons, and then every so often you'll have some carbons that kind of branch off in a different location, like branches on a tree. So this is sometimes what is referred to as a branch chain. And a branch chain basically just means that you don't have all the carbons running together like you do here in a straight chain. You have some branches that come off, again, like a tree. Organic compounds can combine with other atoms besides carbon and hydrogen. And usually what happens is, although the basic backbone of organic molecules are carbons attached to carbons and then hydrogens attached to those, what can happen is we can basically, instead of having hydrogens all the way around, we basically can substitute out 1 hydrogen, 2 hydrogens for some other element. For example, we could substitute out, say, Cl instead of hydrogen. And that gives us other types of organic compounds, that have different characteristics because of what's attached. So the basicness of an organic compound is that carbon-to-carbon bonding with the hydrogens attached. But how we get really a lot of these different functional groups that we'll talk about is we remove 1 or more hydrogens and we add something else in, something like nitrogen, perhaps, oxygen, fluorine, chlorine, bromine. Maybe we make a double bond that happens. So by removing these sort of hydrogens and replacing them with other elements, this is how we basically generate a bunch of our organic sort of compounds and different organic classes of compounds that we see. So here are some common bonding patterns that we see in organic chemistry with different elements. Hydrogen, like we've talked about, is just going to be that one bond no matter where it ends up. As we've also talked about it with Lewis structures, hydrogen should always be on the outside. It should never be in the center. Carbon, like I said, typically likes to make those 4 bonds. And that's a way you could kind of recognize what else is attached by how many bonds hydrogen has, how many bonds carbon has. Nitrogen will sometimes, a lot of times, make 3 bonds and have a lone pair. Oxygen, very common in organic chemistry, will make 2 bonds and have 2 pairs of lone pairs. And halogens like chlorine, fluorine, and iodine will typically be at the outside, filled with their valence electrons as dots. The most common kind of hetero atom that you could have is the carbon-oxygen bond. Hetero means, just like it means with heterogeneous, you see kind of 2 things, 2 different phases. So in a hetero atom, we have some other element bound to carbon. So in this case, it's the carbon-oxygen bond. And again, you can see this is a very common group that we see in organic chemistry. And just the presence of something like that is what makes this a class of organic compounds known as an alcohol. And you might even see the trend, perhaps, alcohol ends in OL. The name of this guy is methanol, which ends in OL as well. So very common things are named based on the groups to which they reside in. Over here, we also see a carbon and an oxygen coming together. And this is also a very common sort of group that we see happen in organic chemistry. The carbon-oxygen double bond is what is known as a carbonyl carbon. The carbon is the carbonyl carbon, our carbonyl group, which is that carbon-oxygen double bond. This is a type of compound that has a functional group of carbon, oxygen, double bond with an H. This is what is known as an aldehyde. IDE. And perhaps you could recognize the last part of the actual name here. This one appears formaldehyde, again, having the very similar sort of name as our group. That's really a common name. These guys actually end in AL when we name them officially. We'll get to that, obviously, in that chapter. So there are some different formulas that are sometimes written. The one here on the left, where we pretty much draw out every single bond to the hydrogen, that is what is sometimes referred to as the structural formula. Our complete structural formula, where you draw out all the bonds to the hydrogen. Another type of formula looks just like this, which is what is referred to as the condensed formula. And that's where we essentially do not draw out all the hydrogens. We have our carbon with our 3 hydrogens, which is here, our carbon with our 2 hydrogens, which is here, our carbon with our 2 hydrogens, which is here, and our carbon with our 3 hydrogens, which is there as well. So condensed formula, we don't draw out the bonds to the hydrogen. We just do the kind of carbon to carbon bond usually is what we do. Any questions on that? All right, so I think we're going to stop there for lecture today. Couple of reminders. Reminder that our next exam is next week. I believe it's on Monday. Again, it will come through on Canvas. Uh, and before Monday, you'll get some instructions on Canvas in terms of how to access the exam, when to take the exam. I think the exam will be scheduled for during our period of time when we normally have lecture and discussion. It will be open for a period of time, a window of time for you to take it and submit the exam. When you see the availability time, what that means is when the end of availability is the last opportunity you would have to actually submit the exam, not start the exam. So if the exam, say, ended at, say, 10 o'clock p.m., and you log in at 9:50 p.m., the computer will only give you 10 minutes to take that exam. So you want to make sure that you log in with enough time that you would get your normal time period, like you were taking it in class, time to do that. So just like in class, if you walked in with 10 minutes to go, you would just have 10 minutes to take the exam. The same sort of thing will happen on the computer. So when you see the end of availability time, that again means that that is the last time you could submit it. Everybody that has any type of accommodations or anything like that, I will put it in. So when you log in, you will get your accommodations in terms of time and stuff like that. So I'll be sure to put all that stuff in. You will need to upload your work. So the test will probably be very much like our regular test. There'll be a multiple choice part where you don't have to obviously show your work or anything like that. You just need to obviously click the right answer. And then there will be a written part where, much like in class, you need to show your work, all the setup, the units, and all that kind of stuff. And then you'll need to, once you finish the exam, you'll need to upload that work on Canvas, and I'll give you instructions on how to do that. But you need to turn your work on a piece of paper that you handwritten your work out for the problems. You need to turn those into a file and upload it on Canvas. And after you've completed your exam. Another important thing is there will be a submit button, obviously, on the exam. You should only hit the submit button once you've completed the entire exam. If you hit the submit button too early or you haven't finished the exam, it will actually give you a warning like, are you sure you want to do this? You left like 30 questions unanswered. So hopefully that will catch your attention. But in case it doesn't, do not hit the submit button until you have completed the entire exam. Otherwise, you'll submit an incomplete exam and it will not be reopened for you. So make sure that you don't hit the submit button until you're ready and you finish the entire exam. There will be a lot of instructions on the exam, so you want to make sure that you read all the instructions. I tried to write down instructions, or again, try to write down instructions for every possible question that you might have or might think about. So I will give you a lot of instructions. So make sure you do read them. And also in each problem, make sure you specifically read each problem and answer it the way it asks you to do so. It is a closed book exam. You're not supposed to obviously work with anybody or anything like that. Just a friendly reminder, there will be different versions of the questions and stuff like that. So just like normal, you don't want to have the right answer on the wrong version or anything like that. When you see the exam, it will be in a module in the Canvas section. And you will have to go through that module in order to allow things to I will know the version of the exam. You won't, so don't worry about it. You don't have to worry about writing the version or anything like that, but I will know the actual version that you get and everything like that. So you don't have to worry about like normal writing the version or anything like that. I will know based on obviously doing it that you know which one you took and stuff like that. So you don't have to worry about that. But there will be obviously different versions and different questions. So you just want to keep that in mind so you don't do anything, obviously, hopefully nobody would, that you shouldn't be doing. But there will be a module to take the exam. And the first thing you have to do is you will have to sign sort of an academic honesty agreement, which outlines all the things you shouldn't be doing when you're taking the exam. You can either print that out and sign it and upload it with your work, or there will be an electronic version where you can kind of electronically sign it if you want. So you don't have to worry about printing it out. So you can do that as well. Then once you've done that, it will open up the exam for you to take. Again, remember, do not start the exam until you are completely ready. Make sure that you have a calculator, something to write with. Once you start the exam, you cannot stop the timer. Even if you click away and you come back, that timer will still continue to go. So make sure you are 100% ready to take the exam before you start, because there's no way to restart the timer. And obviously, if you click away, you really shouldn't be. But if you click away or something like that, the timer will still go. You could then get back to the exam through the module section, click on the exam, and it'll say, do you want to resume? And once you resume, the clock you will have seen will have continuously been moving and stuff like that. So you want to make sure you're completely ready before you start the exam. Once you've completed and submitted your exam, if you go back to that module where the exam is, that will open up the assignment, and you can click on that assignment and it will open up something where you can say submit the assignment, and that is where you will be able to upload your work. The work that you show is like normal. It needs to show all the steps, the units. The same answer that you submitted online should also be on your paper as well. You do have to submit an answer for every question online. If you do not submit an answer for a question online, I will not look at your work on your paper. So you can't just say I showed everything on the paper and didn't put anything online. You have to submit an answer online, and the answer should be matched on the work that you show on the paper. Any questions on any of that? So it will be probably pretty self-explanatory and stuff like that. If by some chance you have any type of question, you should be able to email me through Canvas, and I will be checking my email during that time period, and I'll try to answer your questions. But like I said, everything should be pretty self-explanatory as you go through it. I'm going to try to write the test so it looks very much like the one we've taken in class before. There'll be the first part of the test will be multiple choice. Again, you won't have to show work on that. The second part will be the written portion of the test, where you will have to show work. Every question that you have to show work on will say right there in the question in red, you need to show work for this question. So you'll know exactly what questions you need to show work and what questions you don't need to show work. Any questions on that? The last thing I'm going to tell you is once you submit the exam, the computer will give you a score. Just so nobody freaks out, that probably will not be your final score. What I'm going to do once I go to grade them is I'm going to take the work you upload. I'm also going to check every answer that you put in online to make sure that the computer did not mark it wrong, even though it's right, because it didn't like the way you marked it. So I'm going to check all those things as I go through it. Should take a long time, but I will check all those things, both your online answer and your work. And that also means that on those problems that have work associated with it, you may lose points if you obviously do not show all the work. So you want to make sure you show all the work. This way, again, at least if you put in the wrong answer and you do show the work, I could give you some partial credit and stuff like that. So I will probably make some appropriate adjustments to the score that you see at the end of the exam. Don't freak out. Again, depending on the way you enter it, the computer may mark it wrong, but I will go back and look at every single answer that you do and just double check. Any questions on that? I would also recommend that you do not use anything on your computer like a subscript or a superscript and try to do those things, because I know for sure it does not like when you do that. So just try to enter the answers like I tell you. And usually if it's a numerical answer, you should only enter the answer, the number, with no units online. But when you show your work on the paper, you should enter units. So usually when you enter the answer online for a number, just enter the number. Don't put the units, otherwise we'll mark it wrong. But when you do your work, make sure that you do show the units. I don't know if I can, but we'll see how it all works out. I've done it at my other schools and stuff like that. It's not as bad as it seems. It's just going to be different. You know, I'm probably going to give you obviously a little bit more time than you normally would have, because it is online. You have to read all those questions and stuff like that. So it will be a little bit different, but you know, it'll be kind of the same in that sense. I'm going to try to make it as similar as I can. Any other questions on anything before before we stop this. So with that being said, I'm not going to probably lecture live on Monday. That will open up hopefully this time period for you to take the exam, and you can just worry about the exam. I will be obviously there through email or something like that if you need to email and ask. I will be monitoring the exam during that period of time, you know, and I can see who's taken, I can see how much time you got left, and, you know, I could kind of monitor what's going on my end. So I'll be doing that. And again, hopefully you won't have too many questions, but if you do through Canvas, I think you could just shoot me an email and I'll try to get back to you as soon as I can. Any questions on anything? Okay, a couple other things for discussion tonight. It's going to start a little bit later, so I apologize for that. So probably about 8-ish it might start. Got some things I have to kind of take care of here before I can kind of go back on. So, you know, if you kind of come up for discussion, it may not start until closer to 8, but I will go on at some point and do it. If you want to hang in the waiting room until you see I open it up, you can. If not, I understand as well. But it will start probably a little bit later than normal. So it might be towards 8-ish, okay? Just to let you know. Any questions on any of that? Okay, I will see everybody in a bit. Have a good weekend. If you have questions, feel free to contact me.